All right. Sorry again for being a little bit late. Thanks for joining this session, the call of Ctooling. Um, we're going to talk today about the secrets beyond native image. My name is Edoardo Vacchi. You can find me around on the internet with this nickname. I'll be working in the past as a researcher at University of Milan, then at Unicredit Research and Development Group. It's a bank. You may know it. And now I am at Red Hat, where I work in the Cogito Drools JBPM team. A couple of words about Cogito, the project I'm working on right now. It's a cloud-native business automation suite. You may know it because it's based on rules, JVPM, Opta Planner. Our engines were our traditional engines. We try to reimagine those in the context of cloud-native and the deployment on OpenShift, the Kubernetes, exploit the technologies that are usually used in this context, such as InfiniSpan, Kafka, and it's based on Quarkus. So I'm going to say a few more words about that later, but right now I'm going to talk about native Java. So in order to understand native Java, let's talk a little bit about how Java applications are traditionally run. So when you start a Java application, you have your build time. So you build your application and you have your runtime. Your application initialization phase, it's the last bullet here. But in order to get to that, you have to go through all of these phases that initialize the code that is necessary to actually run your application. And even before you get to the static void main, you already have involved 3 class loaders, 500 classes loads, and about 160 static initialization. We will know more about what those are in a little bit. Now, if you use a framework, then you will have also the initialization of the framework itself, which usually may bring 100 of class loaders, 1,000 more classes, 1,000 static initialization, and then you get to your application initialization, which will bring even more class loader, possibly more classes, more static initializers. So let's take a little bit of history. Native Java compilers are not something new. So even though there's a lot of interest right now for GraalVM and native image building, this is not something that it's completely new. In fact, in the early 2000s, we have prior art using ZCJ, for instance, was a project that allowed you to compile Java source code into native binaries. Then there was ExcelsiorJet, which was a proprietary compiler that took bytecode and compiling to native. And more recently, there was also RoboVM that was targeting mobile runtimes to compile down Java into native. So compilation into machine code is not necessarily something innovative per se, but today it's more interesting. Now, the pros for native code is that it may be faster to start up. It also brings possibly a smaller memory footprint because when you use Java, you need scratch memory to do JIT compiling. What does this mean is that if you are aware of a just-in-time compilation is, basically you are profiling the execution of your application, and then all those code paths that benefit from being compiled into native will be compiled into native. But in order to execute that code, to compile and then execute the code, you have to write it somewhere. And usually you will use the scratch memory, a memory area that we call the scratch memory that resides in your address space. The smaller memory footprint is also because of a possibly aggressive dead code elimination that you can do. And also your executable will be self-contained because you can avoid full JDK class library bundle. You can just bring only those classes that you actually need. Now, considering that historical context, the 2000s, there are quite a few limitations, and thus people were not necessarily embracing fully the idea of compiling into native. For instance, this is not a JDK, so it may exhibit a different behavior than a standard JDK. Besides, it's not cross-platform because you're compiling now into a native binary, so you will have to support every single different platform, and because it's not a JDK but it's a different implementation, it may get out of sync with the specification or with the latest version. Just think of the Android runtime, even if it's not compiling into native traditionally. It's been holding back the Android ecosystem because only an older version of the Java language was supported for a long time. There may be differences in runtime behavior and possibly compromises in peak performance because now you don't have a just-in-time compiler. This can be mitigated by using a technique that's called profile-guided optimization, which basically supplies profile information by analyzing a running application and supplying it to the compiler separately. But it's no longer a dynamic process. It's performed outside of the runtime. Moreover, at that time, application was things that you started once and then run for a long time. Today, what we do, it's kind of different, and we'll see that in a bit. Besides, another thing that the people were saying is that startup time was negligible because application would run for a long time, so you wouldn't restart over and over and over again. So it would dominate, the runtime would dominate over the startup time. And besides, disk was cheap, and also memory. You owned usually your machine. You manage your own your machine, so it made sense to just say, okay, I can just throw more hardware at it and be done with it. And besides, all the benefits that you could get for faster startup time could be achieved using laziness. Now, what's laziness? The idea with laziness is that you don't necessarily initialize your things, your application at immediate startup time, but you delay that initialization in a later phase. So your build time stay the same, your runtime stay the same. The time you get to reach your static void main stays the same because that's JVM overhead, but you reduce the framework initialization time and possibly your application initialization time because you delayed initialization to a later stage. The issue with that approach is that, unfortunately, that makes for a less predictable performance profile because that initialization being delayed could occur at any point in time during your runtime. So that's a trade-off, right? It's easy to achieve, but it may have an impact. Now, the landscape. Today it has changed because we live in this shared managed infrastructure. So we don't necessarily own anymore our hardware, and actually we want to delegate the owning and the managing of our infrastructure to someone else. That means that suddenly we pay per use, and it becomes more attractive to have a faster startup, smaller disk footprint, smaller memory footprint, because we pay for that use. And the fast startup, it's useful because if our application starts up faster, then we can actually shut it down and restore it. So we can actually scale down to zero and pay no cost when our application is not used. Now, how can we achieve these benefits? Well, these benefits can be achieved by generating code and moving some of the processing that we usually do at runtime at build time. Now, how can we do that? Well, we can generate code that basically pre-initializes at boot time the application, and then at runtime we just evaluate that code. Things that we could do: reading configuration time at build time, turning them into configuration commands, and then or read annotation and produce code for dependency injection. This was, in a way, pioneered by some frameworks that were very widely known on Android, such as Dagger 2 for dependency injection, and in general, annotation processor. Micronaut bring that further by using annotation processor everywhere for dependency injection in a microservice framework. And Quarkus developed the idea by making the idea of using GraalVM for native compilation a first-class construct, so to speak, a first-class citizen of the framework. Cogito, I'm putting it here because meanwhile, we were already experimenting with doing code generation to improve our boot time. So now we lay our code base on top of Quarkus, but a lot of things are supported even on a different runtime, Spring Boot, because we do our own code generation. Now, the idea here is that basically we're moving some of the processing that was living here at runtime inside the build time. And to do that, we do code gen. So our build time becomes larger, but then our runtime stays smaller. Now, the downsides of this, the benefits are that, of course, the runtimes becomes tinier. You can even drop dependencies, and that means that your image, your jar, your memory image, your memory footprint will be smaller. But the downside is that you have learned how to do code generation. This can be mitigated somewhat if you use a framework that allows you to do that in a simple way. And Quarkus gives you, for instance, some tooling to do some form of code generation, byte code generation, to be precise, automatically. But that still needs you to learn some stuff. And reflection is so convenient, right? And that's also why probably we abuse it in the Java ecosystem. Now, let me take a small detour and talk about Smalltalk VMs. Smalltalk VMs are somewhat what inspired part of the Java ecosystem, and they have a concept of image, runtime image. So when you boot a Smalltalk VM, you're not just running a program. You're actually starting up a virtual machine that you interact with. You actually write code within the image, within the VM. And what you do is contributing to the VM with code and with the data. So you alter the state of the VM itself. And when you shut it down, it doesn't just go away like it were a normal process without no state. It actually saves the state to disk. And when you restart it, it resumes and restores that state into memory. So it's just like when you close the lid of your laptop and it goes into hibernation mode, or you freeze a VM when you shut it down instead of shutting it down completely. So why am I mentioning this? Well, because of this checkpointing feature of the Linux kernel that's called CRIU, checkpointer restoring user space. It allows you to basically freeze the state of a process and restore it at a later time. There are projects that plug into this mechanism, which is general for any process that runs in Linux, and allows you to it basically gives you an API to plug into that mechanism. And one of those is Crack, which is now also an OpenJDK project. There's Gigawatts, which is a project from our own Christine Flood, another way to provide you with an API to plug into CRIU, and OpenGNI snapshot and restore feature. Now, the way it works is that you're no longer doing any code generation. You do your normal build time, runtime, and your normal boot time here of your application. But then you checkpoint it. That means that you can now restore it over and over again from this point later in time, which means that you won't have to do the boot sequence again and again and again. You will just restart from here. Now, this is as some caveats, because you cannot just save all the states of your application and restore it, because that may be harmful. We'll see that in a bit. Okay, now let's talk about GraalVM, finally. So we're going to see the secrets of GraalVM. GraalVM is an umbrella, though, of technologies, and it includes a lot of different things. Today, we're going to talk about Substrate VM, but GraalVM is primarily a just-in-time compiler, and it's written in Java, which is pretty cool. There's another component you may have heard of, which is the Truffle framework, which allows you to implement dynamic languages using a very high level API. And the thing is, because this API is common across these languages, you can actually then JIT across the boundaries of these languages. Basically, you can have a Python program, a Ruby program, a Java program, and then they will interoperate all together, and they will seamlessly JIT across the boundaries, which is not something that you can give from granted. Usually the JIT is isolated within the language boundary. So what about Substrate VM? Substrate VM is the native image builder. So originally it was called the Substrate VM project, but now it's known as the native image builder. And it does code generation, so it does ahead of time compilation. But what makes a difference from the projects that previously did the code generation and native compilation for Java, it does something that it's static initialization at build time, and it snapshots an image heap. And we're going to see that. So you may probably have heard already about native image compilation, a restriction, a native binary, native image restriction. So there's this restriction about the closed word assumption. What that means is that basically you cannot do reflection without declaring it beforehand, and you cannot do dynamic class loading or actually defining class. And this allows for a lot of aggressive optimization, like such as dead code elimination. You can prune and remove entire parts of your program because you know you will never reach them, even with reflection. And static initializers may not be lazy. Originally, this was the default. Now it's opt-in. You have to say that you don't want your static initializers to be lazy, to be eager. Okay, so let's talk about image heap generation, or how I like to call it, image and heap. Sorry. Okay, this slide and this picture is still is brought to you from the paper Initialize One Star Fast, which is a very readable paper, even if it's an academic paper. The way the native image building process works is that you have this process, this iterative process that points to analysis, running instantiation, heap snapshotting. We're going to see all of them. But basically, it takes the code of your application and generates two things. It generates an executable, your native image, that it's made of two parts. The text section of your executable, it's the code. So the code that gets generated just like a traditional compiler. And the data section contains the image heap, which is basically the snapshot of the state of your application. We're going to see that in a bit. The way this works is that this iterative process takes as its input your application code, but also libraries, JDK code, which is all Java code, and even part of the VM code, because as I said, a lot of the code for GraalVM itself is written in Java, so it can process all of this code together. Now let's see static initializers. So imagine that you have this piece of code. This is a hello world, and instead of printing hello world all in one main, I've broken the hello here and put it in a static block. The reason I wanted to do this is to show you how this behaves differently if you do static initialization at build time. If you do this and run this, if you compile this and run this in a Java VM, what you get is this output, hello and then word, because first the static block will be executed, and then the main entry point will be executed. This is by specification. First the class is loaded, then when you hit the main method, you have to first execute the static method, the static initialization block here. But the interesting thing is that you run this program through native image and you pass this flag, initialize at build time, which for instance for Quarkus is usually the default. You will notice that there's some output, there's a diagnostic code that gives you some information about the compilation procedure, but then there's this odd thing here, this guy that says hello. What's that? Well, let's see. If we run our native executable now, it will just print word, which means that our hello, which is in our static initializer, has been executed at build time. Now, this is very powerful, but at the same time, it can be a problem, and we'll see that in a bit why. But let's go through the details of this quickly. So this is our static block here. And it may look very little. It may look harmless, they're just doing a print. But if you go through it, you will see there's a string load. Then there's a method invocation over a print stream, so you have to resolve that. There's out, which is field, so that's an object. That's a system, that's a class that contains that object. So you have to initialize that class, and you have to initialize all the classes that are involved here before you can actually run that method. All of this has to be done at build time in order to print that hello string at build time. Now, for printing a string, that's not really useful, but if you have to initialize a class, that's extremely useful because it means that you will initialize that at build time and have it ready at runtime. So we mentioned class initializer. The static block here, it's part of a class initializer, but class initializer usually include also initialization of static fields. and they are represented in your bytecode as a special method called CLInit with a square with a angle brackets here. So it's unreachable for regular Java code, but it's reachable from the VM, and it computes these static blocks as much as initial values for static fields. So the developer on GraalVM can decide what parts should be initialized at build time and what should be not. Now, once you have done the build time initialization, you will have a lot of objects laying around in the heap. So what you want to do now is follow all of those objects in your heap and snapshot them so that you can restore them, write them in the image heap data section, then you can restore them at runtime. The way you do that is basically you visit the graph starting from all the root pointers, for instance, static fields, and then you visit all of them. If I have an object which refers another object, which refers another object, gonna follow all these links and construct a collection of all these objects. And then I'm gonna snapshot them and write them inside the data section of the executable. And this is a bit of code from the paper, and actually it's very readable. I'm not going to go through that, so don't spend time reading the code that I put there, but you can find it on the paper, and it's really readable. It's really easy to understand. As for the code generation part, now this is the part that is less, less new in a way. It's the part that is more common across compilers. The points to analysis basically says that you're going to follow your application starting from entry points, which would be static fields initialization, static methods that are reachable, such as static void main, and you start your analysis from those bits of code and follow the code paths. And this is a static analysis, so not at runtime. You don't need to run code to do this analysis. And you follow it and discover all the parts of the code that needs to be compiled. Then you compile them and you bring them to the text code, to the text section of your code. Now, this is an iterative process because as you do points analysis, you may discover new parts that need initialization. And as you do new initialization, you may discover new code that has to be run. So this has to be an iterative process. Now, an example of points to analysis, this is our println, but this requires out. Println requires a string. Out, so you have to initialize that class. Now you have out. Out, it's implementing these interfaces and classes, so you have to initialize all of them and compile them, all of them. And system, it's another class, so you have to compile that, and that refers to other classes, and it may have static initializers, so you have to go and follow those and Okay. Now, how does that work at runtime? Well, at runtime, you will start your executable, and first of all, you will restore your image heap into memory. Now, how this is done in GraalVM is by using memory mapping. So that's very fast. It's just mapping a section of the executable into memory. Now, there's an issue there because pointers will refer to locations of the memory that are no longer valid. So it uses a little trick to use relative offsets to a starting point, and then it will recompute those offsets in a very fast way. But that's an implementation detail. Now, I will mention the perils of static initialization. What about those? Well, this is a tweet by this user, Raibito. He says, "Oh, I upgraded to GraalVM 21.1, and I noticed this. If everything is initialized statically, then if I call random, it will be initialized statically as well. What that means is that the random seed will be basically burnt into the native image, which means if I execute several times executable, it will always return the same pseudo-random sequence, which makes it basically non-random. And of course, the problem with random is that you can never be sure, but that's pretty clear. That's actually a problem. Okay, so you have to make sure that you don't initialize eagerly everything, and this is an example. Now, I'm going to spend a few words about Project Leiden. Project Leiden is a project of the JDK that deals with bringing native image and static images in the specification. So the idea is to address in Java's low startup time, reduce time to peak performance, reduce memory footprint, just like GraalVM native image builder does. But GraalVM native image builder, it's a vendor specific implementation. There's no specification about this. Sorry, it's a vendor specific implementation. There's no specification. So other vendors cannot really implement the same thing. It is open source, but because there's no specification, basically the specification is the implementation. So the idea is that Project Lighten wants to bring this to the JDK as part of the specification, so that other vendors can implement the same procedure. I mean, they can implement a procedure that follows the specification, so they are compatible, and users can expect the same kind of behavior across implementation. And I wanted to mention this project that I've been spending a little bit of my time when I can. But it's a project from a lot of contributors from Red Hat and IBM, and it's open for contribution from other people as well. So it's called Cubic, and it's an experimental sandbox project where people can, when these people can experiment a native image compiler, creating a native image compiler for Java. It's all written in Java itself, and the idea is to experiment with ways to create native image geared towards steering the direction of Project Lighten. So the idea is to work as a sandbox, so that we can experiment with ideas that goes into Project Lighten. It's a self-contained code base, as I said, it was written in Java, and it will allow to experiment with different trade-offs. So we have lesson learned from GraalVM approach, which is now more mature. This is a new project that starts from scratch, but learns from the experiments and the ideas and even the pitfalls that GraalVM explored and pioneered. Currently, it's a Java-based compiler that targets LLVM IR. And that means that it's also able to cross-compile across architecture. So it can compile, it can emit x86 bytecode, or it can, x86 code, or it can also emit ARM native executables, and even on a different architecture. In the future, there could be experiments, and there are ongoing experiments to see if it's possible to change the backend so that it can plug, for instance, the native JDK backend, which is called C2. And these are the links where you can find Cubic if you're interested. Now, this is a very high-level overview of how the architecture for Cubic works. There are different phases, and there are plugins that plug into phases. At each phase, which adds components, analyze, lower, generate, that generates the code, lower, that brings from a high-level representation to the lower-level representation, the LLVM IR. You can plug at different stages so that you can change the contents of what's in the control flow graph that it's being built as you go forward. The idea is that this control flow graph is first created, and then nodes and the control flow graph is iteratively refined by dropping nodes as you go further and further along the line. There's an ongoing discussion topic about static initialization, which some argue it's actually the defining feature of the native image building. And there are different approaches that are being evaluated to avoid pitfalls, such as the one that I mentioned before. For instance, in GraalVM, the idea is that the image is being created and written inside the executable, and then it's used memory mapping plus these offset to point to objects inside the runtime memory. In Cubic, they're experimenting with build time serialization, so a fast serialization and deserialization routine instead of memory mapping. In GraalVM, static initialization was first opt-out, and then it's now runtime first, and it is opt-in only for those components to avoid specifically pitfalls. While in Cubic, currently everything will be done at runtime, and the idea is to bring everything as close to build time as possible. Now, in order to avoid pitfalls, the idea would be to possibly bring language changes to the language to Java, so that people can actually specify what parts of an initializer should be done at runtime and which part should be done at build time. And the idea for Cubic is also to experiment that problem space. I've also so yeah, so that's about Cubic. So I wanted to tell you that the code is there, and if you'd like, you can take a look. A couple of links. So these are the references on which the presentation were based. So feel free to take a look and read that, and watch the Dine Heidinger's presentation on which parts of these diagrams are praised from, which is on QCon Plus 2021. It's a presentation. And also I wanted to mention that the cover art that you see at the beginning is by this artist, Francois Berger, who wrote a great, who illustrated a great book about the Call of Cthulhu. So if you're interested, that's from the cover art. All right, and that was it.
Thank you. Let's see if there are any questions on the chat or. Okay. I'm not seeing any yet.
So if you'd like to ask me any questions, you can still find me on Twitter with Vacchi as an handle. So, and feel free to ask any questions here.
Yeah. Okay, so I guess if there are no questions, yeah.
Thanks, everyone.
Thank you, and yeah, have a good day.
Thank you.
Thank you.